Good morning. I'm Ed Artuni from Lawrence Livermore National Laboratory. The subject of my presentation is the observation of superthermal ions in high-performing ICF implosions. I'd like to thank the organizers of this conference for the opportunity to present a surprising result from recent ICF implosions at the NIF. Many members of the NIF ICF collaboration have made important contributions to this research. In particular, the close collaboration with Alistair Moore, Aidan Crilly, and Brian Appleby has resulted in the work I'm presenting. I'd also like to acknowledge Dave Monroe, who laid the foundation for understanding these results. Jack Steinberger was a major influence in my physics training at Columbia University, being an architect of the department's culture of collaborating, the focus of making experiments work. I've tried to bring this culture to my activities at NIF, and I think successfully. The summary of this talk follows a narrative of developing a diagnostic capability. The initial objective was to develop a technique for measuring the temperature T-ion of the implosion free from unmeasured annoyance parameters. This new method would use a neutron mean kinetic energy shift, a very small part of which is T-ion dependent, but for which all the terms are measured. To perform such an analysis requires determining the neutron time of flight to 40 picoseconds out of 400 nanoseconds, apart in 10 to the fourth. A spectrometer system was deployed to make a neutron velocity measurement to 5 kilometers per second out of 51,000 kilometers per second as a diagnostic of mode 1 perturbations on the capsule. That spectrometer system provided the data for this analysis. The surprising finding from the analysis was that the high-performing implosions could not be explained by Maxwellian behavior, a necessary condition for our proposed technique. This analysis takes place in the energy shift versus temperature plane. The size of the energy shifts are tens of keV, taking place over a T-ion range up to 10 keV. In this plane, Maxwellian behavior is represented by a boundary determined by the DT fusion cross-section. The boundary separates a domain which is accessible to implosions defined here as Maxwellian from a region that is inaccessible to Maxwellian plasmas. Populating this space with 2D hydrodynamic simulations occupies the Maxwellian domain on the plot. Note that as the T-ion increases, the energy shift increases, and the yield increases. This is the expected behavior of our standard model for alpha heating in these implosions. High-resolution 3D simulations followed the boundary. In this case, the neutron spectrum from the simulations averaged over 4 pi are used to determine the energy shift and T-ion. In the 2D simulations, the North Pole and the equator ion moments are used to build the neutron spectrum observables, which are then averaged to determine the energy shift and T-ion. For the data, averaging the neutron spectrum observables from 5 directions determines the observed energy shift and T-ion. The simulation and the data are treated in an identical manner to ensure a direct comparison is possible. The analysis of early ICF campaigns using high-density carbon ablators with cold fuel layers was found to populate the Maxwellian domain. These shots show agreement within experimental uncertainties of the measured T-ion from the variances of the neutron spectrum with the T-ion determined from the energy shift. The data trend suggested that the proposed technique for determining T-ion might succeed. However, there were some implosions that significantly departed from the Maxwellian domain. The results from these implosions initiated a careful study of the detector calibrations, the forward fit procedures, and the detector response characteristics. With the analysis results confirmed, the few outliers were difficult to interpret. The recent shot campaigns, which resulted in burning plasma implosions, revealed that the departure from Maxwellian was a characteristic of these implosions. The energy shift used to categorize implosions provides a ranking consistent with implosion performance with no additional information. For a description of these exciting results from these new campaigns, see Alex Zylstra's invited talk at this conference. The analysis I've introduced is based on our understanding of the dependence of the mean neutron energy on the ion temperature. The expression for the energy shift was derived from Dave Monroe's paper. In that paper, the neutron kinetic energy distribution moments are expanded in terms of the ion relative kinetic energy, the ion temperature, and the ion velocity moments, where the ion relative kinetic energy distribution is Maxwell-Boltzmann. The expression for the Bern average mean of the relative ion kinetic energy can be numerically solved using the DT fusion cross-section and the Maxwell-Boltzmann distribution. The important point to take away here is that the curve is a physical relationship, which holds for DT plasmas described by Maxwell kinetic energy distribution. The averaging of the ion relative velocity weighted by the DT cross-section results in the DT reactivity as a function of T ion. The Bern-weighted ion relative kinetic energy is maximum at the Gamow peak, near the Bern average ion relative kinetic energy. In the T ion range of interest, the average of the relative kinetic energy is 5 times the T ion. The picture we have here is that the ions on the high energy tail of the relative kinetic energy distribution provide the largest contribution to the reactivity. Importantly, the total yield of such an implosion is the reactivity multiplied by the densities of the D and the T ions. However, the average ion relative kinetic energy is determined by the tail ions. We can gain insight by considering the different scales contributing to the neutron spectrum. The relative ion kinetic energy is related to the relative ion velocity in the center of mass of the reacting D and T ions. The resulting neutron and alpha will share the total energy of the reaction, the sum of the relative ion kinetic energy and the energy release from the fusion reaction due to the mass difference of the initial and final states. The neutron share is 14.028 MeV and is the largest contribution to the neutron kinetic energy. Considering this reaction in the local plasma frame, the T and T velocities in the frame can be resolved into a center of mass velocity V and the relative velocity. The final neutron and alpha velocities in the center of mass frame are boosted into the local plasma frame and acquire a component of the ion relative kinetic energy through the boost. In this way, the neutron kinetic energy encodes the ion relative kinetic energy. In Maxwellian plasmas, the ion relative kinetic energy distribution is described by a single number, the ion temperature. The size of the neutron energy shift due to the boost is tens of keV. Assuming the global plasma is described by local kinetic equilibrium, the quantities of T ion and ion velocity become averages over space and time, weighted by the local neutron yield, the Bern average. Vector quantities such as the ion velocity are projected along a particular vector direction, the line of sight, and then averaged. A description of plasma velocity flow fields is described in Dave Schlossberg's PRL. The expected size of these local plasma velocities is of order tens of keV. The lab frame provides measurements of these averaged values, the line of sight neutron velocity, and the variance of the neutron kinetic energy. The energy shift is proportional to a positive radial velocity common to all detectors. The variance is defined as the diagnostic apparent T ion, and as noted previously, has an additional unmeasured term due to the ion velocity variance. The velocity variance terms have associated energy shifts that range from hundreds of eV to as much as a keV. Similarly, the hotspot velocities can provide additional energy shifts up to 100 keV. We can ask what the effect of all this averaging has on the resulting energy shifts and T ion values. The shape of the boundary determines the result of averaging the local plasma values. These local values occupy points on the curve. The average of points on the curve will lay below the curve. Plasmas with local kinetic equilibrium will always average to occupy the region below the curve. If the apparent T ion is assigned to an energy shift, the resulting point will appear below the curve. The apparent T ion cannot be less than the true T ion. The unmeasured ion velocity variance is always positive. Systematic uncertainties of the measurement of the energy shift could put a point above the curve. These measurements are provided by the Quartz-Cherenkov detector neutron time-of-flight spectrometers. The matching dynamic ranges of the gamma ray signal and the neutron signal is the essential attribute of this detector system, allowing both signals to be measured on the same detector. The time difference between the arrival of the gamma rays and the neutrons depends on the unknown neutron velocity and the distance of the detector system from the implosion. The neutron velocity can be determined by the time-of-flight difference. To achieve a fractional uncertainty of 1 part in 10 to the fourth requires timing uncertainty about 40 picoseconds and the distance measurement uncertainty of about 1 millimeter. The neutron kinetic energy uncertainty is plus or minus 3 keV. This precision allows us to investigate energy shift effects of order 10 keV. The QCD system is described in Alistair Moore's 2018 paper. The particle statistics for these implosions has a negligible contribution to the statistical uncertainty of the mean and the variance. For a 10 to the 16 neutron yield, the number of detected neutrons is roughly 10 to the 8th. This leads to an estimated error of the mean of about 0.3 picoseconds. The full width half maximum of the neutron signal is of order 6 nanoseconds at 22 meters. The detector system response has a full width half maximum of 0.6 nanoseconds. The detector response is a small contribution to the measured width. The uncertainty in the detector response contributes less than 100 eV uncertainty to the T-ion measurement. All these detector characteristics are determined from bench measurements as well as in situ measurements using facility calibration shots. The high statistics signals and well-characterized detectors allow for precise determination of the mean and variance of the time-of-flight distributions. Here, a specific line-of-sight signal is shown with the results of the parameterized forward fit, the orange curve. Zooming in on the peak shows the size of the shifts we are measuring. The red dashed line indicates the arrival time of a 14.028 MeV neutron. The magenta dashed line is the shift due to the T-ion, and the black dashed line is the total shift with the addition of the projected hotspot velocity. The black dashed line defines the arrival time associated with the line-of-sight velocity. The kinetic energy scale is also included. Importantly, the relativistic definition of kinetic energy is necessary for providing the precision required in the analysis. Relativistic corrections to the neutron time of flight are of order 10 to the minus 2, and our required precision is 10 to the minus 4. Taking out the shift due to the projected hotspot velocity, the dependence of the energy shift on the variance of the distribution is readily apparent. Here, 3 shots are shown with increasing ion temperature. Zooming in on the peak shows the part of the energy shift due to T-ion. The mean energy shift increases with increasing T-ion for these examples. This illustrates the feature of this analysis for which all the terms contributing to the average energy shift are measured by the diagnostic. This analysis requires that the components of the line-of-sight velocities are separated. A model of the line-of-sight velocity has 4 parameters. 3 parameters for the vector components of a hotspot velocity, which is the motion of the global plasma in the lab reference frame, and 1 parameter for the common radial velocity associated with the energy shift. This parameter is referred to in jargon as V-ISO. The line-of-sight velocities are used to simultaneously fit the parameters for the implosion. The resulting hotspot velocity is used as a diagnostic of mode 1 asymmetries for the implosion, and the V-ISO is used to calculate the energy shift. This analysis is described in a recent 2021 paper. The line-of-sight velocities can provide an independent measurement of the implosion bang time, the time of peak neutron emission. The bang time for each spectrometer is compared with the bang time from the gamma ray history diagnostic, determined to plus or minus 30 picoseconds. The square root of the average difference squared over all the measurements gives a value of 48 picoseconds. This is expected given the 40 picosecond uncertainty in the QCD system added in quadrature with the GRH uncertainty. Importantly, the agreement does not vary over 3 orders of magnitude change in the shot yield, providing a test of the stability of the QCD system operations. The comparison sets the limit on the systematic uncertainty of the energy shift to approximately 3 keV. The GRH system is described in Hans Hermann's 2016 paper. Having established that the detector system meets the measurement requirements, with the estimated statistical uncertainty of the energy shift to plus or minus 3 keV and the systematic uncertainty of the energy shift to plus or minus 3 keV, we turn our attention to the predictions of the simulations. The post-shot ensemble for N180128 is built from the as-shot parameters for the implosion used as a starting point. The simulation inputs are variations of these implosion parameters and produce an ensemble of implosions. The expectation is for the ensemble to provide a conditional probability distribution for the implosion metrics, given the initial conditions. While the ensemble may successfully provide this for many of the implosion metrics, it fails to capture the data results in the energy shift T-ion space. The post-shot ensemble method is described in Jim Gaffney's contributed talks at this conference. This disagreement is statistically significant. Using the ensemble to define the probability that experimental uncertainty could place a point somewhere in the space away from the true implosion parameter, the 99% confidence contour excludes the data from the implosion that was used as the basis of the simulation input. Thus, measurement uncertainties alone cannot account for the departure of the implosion from the Maxwellian domain. Some physics appears to be missing from the simulations. The inclusion of recent shots with yield greater than 10 to the 17 shows a similar trend. For shot N210808, the measured energy shift was 52 keV and the T-ion 12 keV. These two measurements cannot be reconciled within the picture of Maxwellian plasmas. A T-ion of 12 keV would generate an energy shift of 36 keV for a Maxwellian plasma. The average ion kinetic energy would be 44 keV. The energy shift of 52 keV would have been generated by a plasma of 21 keV T-ion. The average ion relative kinetic energy being 58 keV. The increase in the average ion relative kinetic energy observed for this implosion suggests the possible existence of a population of high-energy ions. The population could not be in kinetic equilibrium with the bulk of the plasma, which has a 12 keV temperature. Here we take the 12 keV and 21 keV Maxwell-Boltzmann distributions to estimate the effect on reactivity. Note that the population of ions at average kinetic energy is 0.7% for 12 keV T-ion and 1.4% for 21 keV T-ion, an increase of a factor of 2. The reactivity at T-ion equals 21 keV is a factor of 3 higher than at T-ion equals 12 keV. The existence of these high-energy ions would have to be suprothermal, which is to say, not related to the bulk of the ions in the plasma. The 21 keV T-ion Maxwell-Boltzmann used in this estimate has no physical meaning. The kinetic energy distribution of the suprothermal ion population is not known. But such population of ions could explain the observations reported here, but not included in the physics models used to predict the plasma behavior as indicated in the comparison with the simulation results. Brian Appleby will talk about various ion kinetic energy distributions which could result in the observations at his contributed talk at this conference. We are compelled to look for other explanations for this observation. For instance, we expect the areal density to increase as the implosions improve, and an increase in the expansion velocity at the peak neutron production. The measurement of the radial velocity could be a combination of these two effects. Consider neutrons emitted to the right in the cartoon. The away neutrons are shifted to lower energy and the towards neutrons to higher energy. The detector averages these to a central value with the shifts due to the expansion velocity canceling. However, the areal density for the away neutrons is larger than for the towards neutrons, and that would produce a small term proportional to the product of the difference of the areal densities and the expansion velocity. This would contribute to the energy shift as a true isotropic velocity component. Imagine that the opacity was 100%, only the towards neutrons would be detected, and they would have an additional velocity equal to the expansion velocity. The particle Monte Carlo used in the simulations track a subset of neutrons from birth through the capsule and include these scattering effects. So in principle, such an effect should be seen in the simulations if they correctly can calculate the areal density and the expansion velocities. The 3D codes show no such effect. However, this hypothesis is compelling enough to warrant additional tests, both of the simulations and of the data. The possibility of using DD neutrons, which have a much higher probability of scattering than the DT neutrons, is a project requiring substantial changes to the QCD system and is actively underway. Other possible explanations considered include 1. A shift of the neutron mean energy due to the reaction in-flight tail that populates high neutron energy. Using synthetic data, varying the reaction in-flight spectra would have a contribution much less than the measurement uncertainties. 2. The current forward-fit model parameters include only mean invariance. The neutron spectra are expected to have higher moment contributions, for example, skew and kurtosis. The existence of skew and kurtosis terms have been determined not to contribute to the observed effect for the current implosions. 3. Magnetic recoil spectrometer, MRS, measures the spectrum of the deuteron elastically scattered by the neutrons, from which the neutron spectrum is determined. This spectrometer has very different systematics compared with the neutron time of flight spectrometers. The lack of absolute calibration and plus minus 25 keV neutron kinetic energy resolution limits the significance of the comparison, but the MRS values are consistent with the QCD measurements. Additional work is being considered to improve the absolute calibration of the MRS in anticipation of observing implosions with large energy shifts, which could be resolved by this diagnostic. 4. Yet another alternative explanation involves the physics included in Hydra PMC to account for the kinetic effects of superthermal alphas. This study resulted in modifications of the run parameters to account for the full range of alpha energy loss. The effect of these changes were small compared to the observed values. Many other ideas have been pursued in the course of the research. None provide a plausible explanation. Which brings me to the end of this talk. We have an observation of non-Maxwellian behavior in these high-performing implosions, which we cannot explain. Significantly, the behavior is not predicted by the codes we use to design the implosions, apparently missing physics features to do so. It is not clear if this lack of knowledge affects our ability to design shots. Importantly, we have been able to navigate to this burning plasma frontier unaware of this departure from our standard model of the implosions. So we are left with a surprising result from experiments probing plasma conditions for which we have few examples. It isn't unexpected that surprises may await us as we explore this new domain. Thank you for your attention.